This is the 2012 question number 4 for the BC test. Let's go ahead and read this and do it. So the function f, they tell us is twice differentiable. They give us the value of f at 1, the second derivative at 1, and then in the table they give us selected values. So we want the equation of the tangent line at 1, and then we use this to approximate f of 1.4. It's actually a pretty easy problem. Hopefully we have something like this on the test in May. So part A, you should automatically know when they ask for the equation of a line, you automatically start with your standard form. Y minus y1 is mx minus x1. And they tell you the point, x equals 1. And in the problem, they already tell us y is 15. Y. This is freaking out again. So that was easy. Then we need the slope. You should all know the slope of a tangent line is the derivative. So we need the derivative of f at 1. But that is given in the chart as 8. So now we just plug everything in and we're done with part A. You do not have to we actually do in this case, because they want us to use this to approximate f at 1.4. So we're going to isolate y. We're going to get 8x minus 8 plus 15, so that should be plus 7. Now, f of 1.4 is going to be approximately equal to y of 1.4, which is 8 times 1.4 plus 7. Do not simplify that. That is an acceptable answer. Remember, if you simplified it incorrectly, you lose the point that you already had. So you should leave it like that. All right, part A, we're done. Part B is going to take some work. I'll do it up here, so I'm going to cover all this. Use the midpoint Riemann sums with 2 subintervals. Nice, it's only 2. And we're going from 1 to 1.4. So our two intervals will be 1 to 1.2, 1.2 to 1.4, since they want 2 subintervals. And we want to approximate the integral. This is actually pretty nice. There's not too many to write out. Don't forget your squiggly equals, because we're doing approximately. And then midpoint. You know what? I'm going to go ahead and show you a visual picture of what's going on for midpoint, because some of you have trouble with this one. So if we have a graph, and that's not this graph, I'm just drawing a random graph, and we're breaking up into 2 intervals. Well, you take the midpoint of each interval, and that's the height of your rectangle you're going to use. Take the midpoint. That's the height of the rectangle you use. So just find the height in the middle, and that's your height of the rectangle. So the middle of 1 and 1.2 is just going to be f prime at 1.1, and the width between those two is 0.2. That's the width of your rectangle. Your second rectangle, the middle, occurs at 1.3. So you want f prime at 1.3. And the width of that, again, is 0.2. Now we're going to plug in our actual values. It's going to be 10 and 0.2 and 13 and 0.2. We're done. You don't have to simplify that. That is your answer for part B. Well, the first part of part B. If you wanted to, but you shouldn't, you can simplify that to 4.6. Let's go ahead and keep reading. Then it says, use the approximation that we just found to estimate the value of f at 1.4. Oh, I see where they're going with this. Fundamental theorem of calculus. So here's some information. We want f of 1.4. We have f of 1 is given. So this is fundamental theorem of calculus. So f of 1.4 is a starting value. So we know the starting value, f at 1, and we need to know how much f changes from 1 to 1.4. But if you integrate f prime, that tells you the change in f. So we're going to integrate f prime. Well, f of 1, that's given. That's 15. The integral we just found in the previous problem, 4.6. So simply 19.6 is our approximate value using our Riemann sum. All right, that is part B. This one's going pretty quickly. 2 more questions, part C and D. Part C, Euler's method, 2 steps. I like that again, not a lot of steps. So we just need 3 columns because we're doing 2 steps. I need my x value, my y value. That's not y. My y value, my delta x, my dy dx, and my delta y. So my starting value, they tell us at 1. So 115 is our starting value. We're going to end up at 1.4. That's our using 2 steps. So our delta x is going to be our change in x, 1.4 minus 1, 2 steps. So it's going to be 0.2. So that's going to be each of our delta x's. So dy dx, wow, that's pretty easy. Just look at the chart. dy dx at 1 is 8. 8 times r, so we're going to multiply these two to get our delta y. So it's 1.6. Add that to the y. That's going to be 16.6. So dy dx at 1.2, again, we just look at the table. It's so easy. 12 times our delta x. That's going to be 2.4. Add that to our y. That's going to be 19. So that's our answer. So f at 1.4 is going to be about 19. All right, let's do part D and we'll be done. Second degree Taylor polynomial. Wow, I like this. Not too bad. Second degree. So we're just going to create a Taylor polynomial from scratch. So that's going to be, and it's about 1. So it's going to be f of 1 plus f prime of 1, x minus 1, plus f double prime at 1, x minus 1 squared over 2 factorial. This is over 1 factorial if you want. 0 factorial if you want. But that's it. Just let's plug in these numbers. They're all in the table or somewhere. F of 1, that's just 15. F prime of 1 from the table is 10. And F double prime of 1 was given right here, which is 20. That is our second degree Taylor polynomial. Our last step, we're going to approximate f of 1.4 using our Taylor polynomial. So it's going to be our second degree Taylor polynomial at 1.4. Just plug those numbers in and it's finished. That is our answers. And for you fools that simplify, you should get 19.8. That's it. Bye.